Good morning everyone. My name is Deepak Bakal. I am a PhD student in mathematics at Savitribai Phule Pune University, India. I have recently submitted my PhD thesis and currently I am working as an assistant professor in the Department of Applied Sciences at COAP Technological University, Pune. This talk is based on joint work with my PhD supervisor Professor Y.M. Borse. In this talk, I will be discussing the hardness results on bondage and reinforcement problems in chordal graphs with a particular emphasis on the split graphs. Let me begin with the basic notation. A dominating set is a set of vertices that covers the whole graph G in the sense that every vertex is either in the set or is adjacent to a vertex in it. The minimum size of such a set is called the domination number of the graph G. Domination number is a fundamental graph theoretic parameter which finds numerical applications in facility location, network design, communication networks, etc. Naturally, whenever a graph parameter becomes important in practice, it is essential to understand how stable it is under the modification of graphs from an algorithmic perspective. Thus, it is an interesting and important problem to recognize the impact on the domination number when graph is modified through various operations, and this has been extensive studied in the literature for deletion of an edge, addition of an edge, contraction of edge, subdivision of an edge. And in this talk we will be focusing on the first two, namely the addition of an edge and deletion of an edge. So let us begin with the definition of the bondage number. So if I delete the edge E from the graph G, then since every dominating set of G minus E is also a dominating set of G, we get that the gamma of G minus E is greater equal gamma of G. Thus, the domination number of the resulting graph either decreases or stays the same whenever the edge is deleted. The bondage number of a graph denoted by B of G is minimum number of edges whose removal shall increase the domination number of G, whereas the reinforcement number is the minimum number of non-edges whose addition would decrease the domination number of G. In the decision version of these problems, we are given a graph and an integer k, and we are asked whether the number of required modification to increase or to decrease the domination number is at most k. So these parameters were introduced as early as 1990s and they have been studied extensively from the combinatorial perspectives. However, their algorithmic and complexity theoretic aspects were investigated much later. Hu and Zhu initiated the algorithmic study by proving that both these problems are NP-hard on general graphs. Hu and Son later strengthened the NP hardness of both these problems for bipartite graphs, and recently Bouquet studied the complexity of bondage problem on planar graphs. And despite these developments, the computational complexity of bondage and reinforcement on chordal graph has remained unexplored. In this talk, we will be proving that the bondage and reinforcement problems are NP-hard as well as co-NP-hard on split graphs. Split graphs is a particular case of chordal graphs in which the vertex set can be partitioned into a clique and an independent set. And a useful property that is used throughout the proof is that the dominating set of a split graph can be assumed to be contained entirely in its clique. So for instance, here I have a split graph with 6 vertices v1 to v6 forming the clique and the 8 vertices u1 to u8 forming the independent set. And if I were to dominate the vertex u1, I would have included either u1 in the dominating set or one of its neighbor v1 or v2. So if I include u1, it dominates the vertex v1 and v2. The same result I can get by including vertex v1, since it also dominates the vertex v2 and the vertex u1. So it is always better that I include the vertex from the clique by replacing the independent set vertices. In this talk we will prove that the bondage problem is NP hard as well as co-NP hard on split graph 7 when k equal to 1. We will prove that the reinforcement problem also remains NP hard on split graph 7 when k equal to 1 as well as co-NP hard. And this, as a consequence of these results, we settle the conjecture of Hu and Su. They had conjectured that both these problems do not belong to NP, and under the standard complexity theoretic assumption NP not equal to co-NP, our hardness result confirm this conjecture. They had also asked to find the polynomial time approximation algorithm with performance ratio as small as possible. What we have proven is that the performance ratio should be strictly greater than 2. Anything smaller than 2 is not possible. So I'll sketch the proof of the NP hardness of the bondage problem by describing a reduction from 3 sets. So for each literal u, I'll include the literal vertices ui bar. I'll make a new vertex v1 adjacent to both u1 and ui bar. For each clause I'll include one clause vertex and I'll add the edges as per the containment of the literals. Then I'll include the new vertex pqr in the dominating set, and I'll make this vertex p adjacent to all the clauses c1 to cj. Then I'll include the two new vertices a and b. I'll make the vertex a adjacent to the vertices p and q, and I'll make the vertex b adjacent to vertex q and r. And finally I'll form the clique of all these vertices. So this way all these vertices form the clique and these vertices form the independent set, and this is a split graph. Notice that in order to dominate the vertex v1 I must include one of the vertex u1 and u1 bar, and in order to dominate vertex b I must include vertex q or vertex r. Thus the domination number of g will be lower bounded by the number n plus 1. On the other hand, if I include the vertex u1, u2, un, the vertex p which dominates all the clauses, and the vertex q, then I get a dominating set of size n plus 2. Thus the domination number of g is squeezed between two numbers n plus 1 and n plus 2. Now I claim that the set of clauses C is satisfiable if and only if the domination number is n plus 1. If C were satisfiable, then I know that each clause contains one true literal vertex. So for each clause, if C is satisfiable, I'll have a satisfying truth assignment. All the true literal vertices, I'll include them in the dominating set. Once I include these vertices in the dominating set, these vertices have taken care of dominating the vertices v1 to vn, and they have also dominating the clause vertices c1 to cm. And now I'll include the vertex q in the dominating set, and this way I get the dominating set of size n plus 1. On the other hand, if the domination number was n plus 1, I know for sure that the vertex q was included in order to dominate vertex a and b, and exactly one literal from u1 and u1 bar was included, and the vertex p was not included. Thus all the clause vertices, if they were dominated only by the corresponding literal vertices, and I get a satisfying truth assignment. Now if I delete any edge from this graph G, then every resulting graph, the domination number will be less equal n plus 2. I can do this by going through all the possible cases. Now the next claim says that the domination number of this graph G is n plus 1 if and only if the bondage number is n plus 1. So if domination number of this graph is n plus 1, if domination number of this graph is n plus 1, and if I delete the edge q comma b, then the domination number of this graph G minus qb, I must include the vertex are I must include one of the vertex p comma q, and I must include one of the vertex ui and ui bar. So the domination number will be at least n plus 1, and I can show that it is exactly n plus 2, and thus the bondage number is n plus 1. On the other hand, if the bondage number is exactly 1, then I know that there is some age such that gamma of g is strictly less than gamma of g minus e. Now gamma of g minus e by claim 3 is less equal n plus 2, and by claim 1 I have n plus 1 is less equal gamma of g. Thus gamma of g turns out to be equal to n plus 1. Thus by claims 2 and 4 I have established that b of g is equal to 1 if and only if c is satisfiable, and hence the bondage problem is NP hard on split graphs. Now we will prove that the bondage problem remains co-NP hard. We will do so by establishing that b of g is strictly greater than 1 if and only if c is satisfiable by going through the construction established in this graph. The graph is a slight modification of the previous construction. So notice that for this graph the domination number is n plus 1. I'll include exactly u1, I'll include u1, u2 up to un in the dominating set, and I'll include the vertex p. This vertex p dominates all the closed vertices and the vertex a, and this way the domination number of this graph is n plus 1. Now the next claim is that the bondage number is strictly greater than 1 if and only if c is satisfiable, and the key part is that if I delete the edge pa, then I must include the vertex q. The vertex p remains absent from the dominating set, and if p is not included, then in order to dominate the clauses, if the domination number has not to increase, then this has to be a satisfying truth assignment. So this way we can establish the claim 2, and this proves that b of g is strictly greater than 1 if and only if c is satisfiable. Thus the bondage problem is co-NP hard on the split graphs. For the reinforcement problem, the core idea and the logic is same. We give the reduction from 3 sat. The graph is like this. We prove that the domination number is n plus 2, and then we will show that the reinforcement number is 1 if and only if c is satisfiable. The key idea here is to add an edge q comma a, and this way we prove that reinforcement is NP hard, and then we can also show that this problem remains co-NP hard by slightly modifying the previous construction as follows. For this graph we will prove that the domination number is squeezed between n plus 1 and n plus 2 as previously. Then we will prove that it is n plus 1 if and only if c is satisfiable, and then we will prove that c is satisfiable if and only if r of g is strictly greater than 1. So as a consequence of our result, we have proven that the bondage and reinforcement problems are both NP hard and co-NP hard. So since if the problem is co-NP hard, and if the problem was in NP, then it would have immediately implied that NP equal to co-NP. Thus assuming NP is not equal to co-NP, we have settled the conjecture of Wu and Su that these two problems do not belong to NP. They had also asked to find the polynomial time approximation algorithm with small performance ratio. Now any polynomial time algorithm with performance ratio less than 2 can identify the bondage number equal to 1 case in polynomial time. Thus there is no polynomial time algorithm. This would lead to p equal to np, and thus there is no polynomial time 2 minus epsilon approximation algorithm for either of these two problems. Since the problems are NP hard for k equal to 1, both these problems are para NP hard and they do not admit FPT algorithms or XP algorithms parameterized by the solution size on split graphs. However, by using the fact that the dominating set is FPT parameterized by the click width and the fact that the addition and deletion of an edge changes the click width of the graph at most by 2, we can prove that the bondage number equal to 1 or deciding if reinforcement number equal to 1 is FPT parameterized by the click width of the graph. And for every fixed k, we can show that deciding if b of g is less equal k is FPT parameterized by click width by using the same brute force approach. However, if this k is part of the input, this is merely an XP algorithm. This brute force algorithm is merely an XP algorithm. It thus remains an interesting open problem to obtain whether the combined parameter k plus click width of g admits a FPT parameterized algorithm. Similarly, it is an interesting problem to decide whether the bondage and reinforcement problems are W1 hard when parameterized by gamma of g. Thank you for your attention, and these are some of the references. Thank you. Any questions, I'd be happy to answer.